Okay, so here's where we left things. We have hypotheses. The population of all cars on the road, 23% are uninsured, or it's bigger than that. We found a p-value. What's the probability that we would get a p-hat of 30% or larger if this was true from our sample? Let's go back and look at the hypothesis test template. The null hypothesis, pi, is 23%. We had 126 cars, 38 were uninsured. That's 30.2% uninsured. And our p-value was 2.81%. And we didn't really do anything with that other than say, well, that sounds unlikely. Well, unfortunately, we do have to make a conclusion. We have to, down here, either the null hypothesis is wrong or it's not. Sort of. Let's first look at the situation we've got. In the real world, out in the population, the null hypothesis is either true or it's false. In this case, the proportion of cars uninsured is either 23% or it's not. We have to, down here, make a decision and say, we reject this, and conclude the researcher's right, or we can't reject this and we aren't able to show. It's not that this is wrong, we just can't show it. So even though one of these two things is true, we have to do one of these two decisions. If the researcher's right, so this is the real situation, the researcher's right, and we reject the null hypothesis, then we've made a correct decision and a correct conclusion. But what if the researcher's right and we say, that doesn't look that far out there, I'm not going to reject that null hypothesis. We've made a mistake. The opposite could be the researcher was wrong. The null hypothesis is true. The population proportion actually is 23%. And we look at our value and say, that looks pretty big. I'm going to reject that null hypothesis. Well, then we've made a mistake. Or we could say, yeah, that 30% is not that far away. I'm not going to reject the null hypothesis. Then we've made a correct decision. Now these two errors have special names. A type 1 error is rejecting the null hypothesis when it is true. We haven't defined the level of significance. We're going to see that in a minute, but we actually get to pick that. We can pick up front what is the probability we're going to make this mistake. A type 2 error is that we fail to reject. Some people actually use the word accept. I put it in quotes. Technically that's not what we do, but we fail to reject the null hypothesis when it's actually false. We just didn't know it. It's difficult to control for that probability because there's many things we can't control, but that's what's out there. So my chart gets updated. If in the real world the null hypothesis happens to be true, back to our car example, if in the real world 23% of cars are uninsured, and we reject that hypothesis, we have made a type 1 error. If we fail to reject it, we're good. Now if in the real world 23% of the cars are not uninsured, it's greater than that, and we reject the null hypothesis that says it's 23%, then we've made a correct decision. If we fail to reject it though, now we've made the type 2 error. So let's go and look at kind of where these things come from. This is a different sheet we haven't looked at yet. There's a lot of different distributions here, even though you can't actually see them all. So we set this up so that the world actually is 23%, and we're going to take samples of 128 vehicles at a time. So this saying, there's the hypothesis, this says it's true. The actual population proportion matches the hypothesis. So notice over here it says it's true. So we're in this world. We haven't made a decision yet because there's no sample data here. But what we choose is how far out here does the sample value have to be to say, that's really unusual. I don't think it happened. I'm going to reject this. Go back to this one. How far out, this is the sample, how far out does this sample have to be? This would happen this far or further only 2.81% of the time. At a 5% level of significance, the way we make the decision is we literally compare these two numbers. If this number is smaller than that, if the p-value is smaller than the alpha, the level of significance, we reject the null hypothesis. I'm going to go through all of these with an alpha of 5%. Since the p-value, which is 0.0281, is less than alpha, which is 0.05, we reject the null hypothesis. There is evidence that the proportion uninsured cars is greater than 0.23. This is a formal statistical conclusion. We don't know that we're right though, because we don't know what the population actually is. All we have is our sample. There is a chance we've made a mistake. Because, remember what this p-value is. It's the probability of getting something this big or larger when this is true. So there's a 2.81% chance we're wrong. In this case, since the p-value is less than alpha, we reject the null hypothesis. Yes, that sounds very repetitious, but it's good practice to get into that. It's evidence that the proportion of shoppers who use discount coupons is greater than 0.66. Again, we don't know for sure. This is an extremely small p-value, so I really feel pretty good about the decision, but I don't actually know because there is a 0.0004 or a 0.04% chance that this could be true, and I would have got a sample this big or even larger. Since the p-value is less than alpha, we reject the null hypothesis. There is evidence that the proportion of adults who drink milk is not equal to 0.90. We only had a not equal, so our conclusion can only be not equal. And finally, the opposite. Since the p-value is greater than alpha, we fail to reject H0. If you want to emphasize that, go ahead and emphasize it. There is not evidence that the proportion of Southern Kentucky University students accepted to medical school is less than 0.46. It sounds like it's a double negative, but in the statistical world that's actually an okay statement. This wasn't far enough away. That p-value says it's too likely this could happen. Now, I did all these with an alpha of 5%. So let's go look at this again. We drew a line in the sand, and that's what statistics does. That says if I get past here, I'm going to reject the null hypothesis. And we can look at the picture and say, but that means there's quite literally a 5% chance I'm going to do that and make that mistake. So it would make sense to go with a stricter level of significance. Certainly I'd rather have this probability of making a mistake than this probability of making a mistake. However, this picture is still under the column that the null hypothesis is true. What if the null hypothesis wasn't true? What if the researcher was right, and let's say that 28% of cars on the road were actually uninsured? Well, the null hypothesis is still this black distribution, but the real hypothesis, or the reality, is this green distribution. That red is still the line in the sand that we drew. So anything this side of the red, we're going to reject the null hypothesis. In this case, that would be a correct decision, by the way. So if I land out here, good. I'm now in this column of reality. The null hypothesis is now false. So if I land here, great. But what happens if I don't? If I land on this side of that red line, I'm going to fail to reject the black graph. I'll think the null hypothesis is still true. Well, what's the probability under the green reality graph of landing on that side of the red line? Well, it's actually right there, and it's pretty high. They call that beta. It's 61%. So if the real world is only 5% away from the hypothesized world, there's a 61% chance my test won't show it. Power is simply 1 minus beta. Power is essentially the probability that you will see a shift. So alpha only matters when the null hypothesis is true. If the null hypothesis is false, alpha is not an issue. But beta changes based on how false it is. If the reality was way higher, well, now my beta is pretty small. It's just this tail. Remember, the red line hasn't changed. That's the null hypothesis that we think, well, now it's not true anymore over here. So if we land this side of the red, we will reject the black hypothesis, the black graph. If it's on the other side of the red, we'll fail to reject the black graph. That isn't very likely. In fact, it's less than 2%. But the reality is very far away from the null hypothesis. The closer reality is, the harder it is for the statistical test to know it, the less powerful the test is. What if reality is only 3? What if reality is only 2%? What if instead of 23% of the cars being uninsured, 25% of the cars were uninsured? It's going to be very difficult for this test to see that, and we're very likely to make a type 2 error. So I can't control that. I can't control reality. Whatever the hypothesis is, and reality is whatever it is, and the more different reality is, the smaller the chance of a type 2 error. We can control the sample size. It costs more money, but if I get a larger sample size, I reduce the probability of a type 2 error. Reality in this case is still very close to the hypothesis, so it's still hard to see it, but I've reduced the probability of a type 2 error from 86% to 79%. Of course, it gets more expensive to collect more data. So beta, I can't pick it like I can alpha. It depends on how large my sample is and how far away reality is. But alpha, I get to choose. because I start my process by assuming that all hypotheses are true and the entire statistical significance test process assumes that all hypothesis is true until I get a small p-value and say, I guess that all hypothesis wasn't true. Over the years, statisticians have decided 5% for alpha is a pretty good compromise. The problem, you go back to the stricter alpha, goes back to what if the null hypothesis is actually false. The smaller my alpha, the bigger my beta gets. If I'd had this cutoff of 5% alpha, I'd only have a 35% chance of a type 2 error. But if I'd gone with the stricter alpha, I increased my type 2 error to almost 60%. So I can't have both be small unless I get monstrously large samples. So over the years, 5% works. Sometimes you'll do 1%, sometimes you'll do 10%. In most cases it'll be 5%. Unless you're told otherwise in this class, assume alpha is 5%. And then I can actually make the conclusions. Let's do some with means just to see the process. So here's a question. We've got a certain brand of store stocking products over a sample of 30 shifts, and we got their performance. The mean number is the sample mean. The standard deviation, a sample standard deviation, it says the industry standard is 496. These clearly are not the same number, but that could be random variation. So is this evidence that this store's performance is below the industry standards? So there are my hypotheses. At a population level, is Bose equal to the industry standard, or actually, it's backwards, below the industry standard? Let's go back to our hypothesis template. Let's look at that menu. We're doing single sample testing for proportions and single sample testing for means. That's all we have going on here. So here's the setup. So in this problem, mu is 496. We'll stick with the 5% alpha. Our x bar is 491. Our sample was 30 shifts and our standard deviation was 12.56. Now some differences all of a sudden are we see a t instead of a z, and this says this is a t distribution. We don't see the sampling distribution. This was covered some with confidence intervals. Once I start dealing with x bars, I can't just substitute s for sigma without paying somewhat of a penalty. And instead of that normal distribution, the standard normal z distribution, I get something called a t distribution that changes slightly based on the sample size and the degrees of freedom. T distributions, there's a whole subject about those, but for our purposes it's very much like the standard normal and it's close enough to what we want to do. So that's how we do the work. So our alternative hypothesis in this case was one-tailed. So we look at the one-tailed p-value and it's 0.0188. Well, that's less than 5%. So the p-value is, I already forgot what it was, 0.0188. Since this is less than alpha, we reject the null hypothesis. There is evidence that Super Bose performance is below the industry standard. Now you may look at this and say it's not that far below, I'm not too worried about it, and that's a valid question. Whether or not this matters, being off by a few, is a different issue. But statistically we're saying this variation, this observation doesn't match expectation, this variation is not likely to be random. There's only a roughly 2% chance I'd have a variation this big or larger. So my conclusion is reject the null hypothesis. Here's another one. I'm doing location analysis. We're going to build the shopping center as long as the mean income is above $45,000. So there's a hypothesis. Null hypothesis. The mean is $45,000. Alternative hypothesis or research hypothesis, it's greater than $45,000. So we can set that up. We're going to go back over here. 45,000. We'll leave the 5% alpha. We don't have our data yet. So I got a sample of 49 homes. The sample mean was 46,957. And the sample standard deviation was 6,785. It was a one-tailed question, greater than. So I look at the one-tailed p-value. There it is, 2.45%, 0.0245. Since 0.0245, the p-value is less than 0.05 alpha, or the level of significance, we reject the null hypothesis. This is evidence that the mean household income in the area is greater than $45,000. At a practical level, what this means we will build the shopping center. So let's talk about type 1, type 2 error again now. The p-value, remember what it means. Let's go back over here. It means there's a 2.45% probability that if this is true, we'd get an x-bar this big or bigger. In other words, there's a 2.45% chance that this actually is true. And I just said we're going to reject that and build the shopping center. So if we made a type 1 error, then we're going to build a shopping center that will not be profitable. You have to think about what the implications of type 1 and type 2 errors are. Now let's suppose we'd actually had a different result. Let's suppose our result had been $45,957. With the same standard deviation, we'd be sitting here. And we'd say, you know, this really isn't very far out there. This doesn't look extreme. Look, the p-value is 16.43%. We'd have a different conclusion. We'd say since 0.1643, since 0.1643 is greater than 0.05 alpha, we fail to reject H naught. This is not evidence the mean household income is greater than $45,000. We will not build the shopping center. If this were a type 2 error, then we'd be passing up on a profitable shopping center. You can't avoid type 1, type 2 error. You just need to be aware that they're out there and that no statistical decision is ever absolutely guaranteed. That's one reason they're called probability values, but you still have to make them. So now we've gone through the process, studying the hypothesis. You select a level of significance. We almost always use 0.05, that's alpha. Then we get the sample. The conditions are largely, is the sample random, and is the sample large enough? For questions about means, if your sample is at least 30, it's large enough. For questions about proportions, if you have at least 5 yeses and 5 nos, it's generally large enough. Then we compute our test statistics and p-value. The software computes the test statistics and p-values for us. We look at the p-value, compare it to our alpha, and state a conclusion, knowing that we could have mistakes. It's not perfect, but it's the way statistics works.